Hello, welcome to this video. In this session, we will study the applications of Gauss law of electrostatics and learn how it can be used to determine the electric field due to point charge, line charge, and surface charge distributions. Myself, Dr. P.V. Rajshekar, Professor and Director IQAC, School of Sciences and Humanities, SR University, Warangal, Telangana, India. These are the key learning outcomes from this video. Apply Gauss law of electrostatics to the three types of charge distributions, point, line, and surface, thereby to calculate the electric field intensity due to various types of charge distributions. Let's start with point charge. Charge with point dimension. Let us consider the charge is kept at a point Q at a point P, let's say. Now we want to find out the electric field intensity at a point here on the surface, which is at a distance r. Now what we do is to determine uh, electric field intensity due to a point charge q, we construct a Gaussian surface which is spherical in nature. Here on the screen it appears as a circle, but it is practically a sphere. Gaussian surface is an imaginary surface. We imagine it encircling the point charge symmetrically around all sides. So in order to use Gauss law of electrostatics, we must have that closed surface enclosing this point charge or any other type of charge distributions. So in this case for point charge, the suitable one is a spherical because it encircles the point charge equally from all sides, symmetrically from all sides. Now what we are trying to do is, there is this point at which we want to find out the electric field. So we have considered an elemental surface ds, the vector projected, and the electric field both are in the same direction because electric field due to a point charge is always radiating outward, especially if it is the positive charge radiates outward, and if you consider any surface and you project the normal, both will be in the same direction. Essentially, this understanding we need to have whether we do it for point charge, line, surface, or any other type of scenario for which you are trying to find out the electric field intensity. So point charge is the simplest case out of all, where you are trying to find out the two vectors, the normal drawn to the ds as well as the electric field, how both are. Because essentially if you see that ds cos theta, e ds cos theta, actually it is e dot ds dot product e ds cos theta. So you should be knowing what is the angle. Is it 90 degrees or is it 0 degrees? That decides the value. If it is 0, cos 0 becomes 1. If it is 90 degrees, that contribution doesn't arise at all. So that's the purpose with which we need to find out what is the angle between the two vectors. And also the crucial thing is considering this imaginary surface, the Gaussian surface. In this case for point charge, it is the spherical Gaussian surface. Now let's look at the mathematical treatment. How do we do it? It always starts with the Gauss law. Integral EDS is equal to Q by epsilon naught. That's what we have been seeing. E dot ds is resolved as E ds cos theta is equal to Q by epsilon naught. One should remember that we should start with the Gauss law. Eventually, we need to find out the electric field intensity. That's the purpose. That's where the similarity in all these point, line, and surface charge distributions we will be following. We'll start with the Gauss law. We end up with finding out the electric field intensity. So ds and E are in the same direction. Therefore, the angle between them is zero. That's what we have discussed just a while ago. So one should be having a clear understanding of what is the angle. Is it zero or not? So that makes us see that certain components contributions remain, certain other contributions become zero. That you will understand in our next scenario cases, which is line charge and the surface charge. So what happens is this cos theta is zero, cos zero is one, therefore what left out is EDS is equal to q by epsilon naught. So E is a constant. Because charge is constant, the electric field due to the charge is also constant. E comes outside. Integral ds. So what is this ds? The elemental surface that we have considered on this spherical Gaussian surface. So one should remember that it is spherical Gaussian surface is equals to q by epsilon naught. What this integral uh, integral ds represents, that you are trying to find out the total surface area of this sphere, because this elemental surface, if you increase further, what it does is eventually it covers the entire surface area of the sphere. So what we are trying to get is the total surface area of the sphere. So that is known from the basic understanding that 4 pi r square, where r is the radius of the sphere, connecting the charge which is at the center of the Gaussian surface to exactly the surface. It is touching the surface. So that distance is r. Essentially, it is the radius. So E into 4 pi r square is q by epsilon naught. Then E is equals to, if you take it to the other side, entire thing, it is 1 by 4 pi epsilon naught q by r square. And if you cross multiply epsilon naught with E, then that we call as electric flux density. D is equals to q by 4 pi r square. So what we have done is we haven't used the Coulomb's law, but still we have obtained the expression for electric field intensity. That's the beauty of Gauss law of electrostatics. Uh, you have seen that with Coulomb's law, you'll get the force of attraction or repulsion between two charges. Once you get the force expression for force, then you will get the expression for E as F by Q. E is equal to F by Q. So we need to know the force between the two charges, and the limitation to uh, Coulomb's law is that it is valid only to point charges, point static charges. For this, you can watch my another video on Gauss law of electrostatics. Uh, but here we didn't calculate the force, but still we got the electric field um experienced by any charge kept at the surface of the Gaussian surface which we have considered, spherical Gaussian surface which we have considered. So now with this understanding, what we have done is we started with the Gauss law of electrostatics, and then we have seen what is that angle between the two, the electric field as well as electric field in which direction, and normal to the surface which direction. So if both are in the same direction, you got zero, angle as zero, and cos zero has become 1. Then we have tried to calculate the integral ds, total surface area of the spherical Gaussian surface that we have considered, and that has led to the expression for electric field intensity. So there will be more complex scenarios, but this is the simplest case of all. Now the second one is, let's have a look at the line charge. You know what is line charge? it's one-dimensional charge spread across this line. So we can also call it as infinite line charge extending to infinite. So even if it is finite or infinite, it doesn't make any difference. Towards the end, when we get the formula, you will also understand and appreciate the fact that the length of the line charge doesn't matter here. So when we talk about the line charge, when we talk about the point charge, it is a charge that we say is Q. When we talk about the line charge, we need to know line charge density. Per unit length, how much charge is present. Just like density is mass by volume, charge density is charge by volume, but we are talking about line charge. Line charge density is charge per unit length. So if you take any unit length, how much charge is present? So that is line charge density. So when we talk about line charges, we don't say Q, we say rho L. So we essentially should be knowing how much of charge is present per unit length. Now, just like in the previous case, for point charge, we have considered a spherical Gaussian surface. The idea is that the Gaussian surface should be encircling it symmetrically on all sides. Just like that, in case of a line charge, we take a cylindrical Gaussian surface. Why cylindrical Gaussian surface? It's that if you take a cylinder and exactly at the center of the cylinder, if you imagine a thin wire passing, and then what happens is that thin wire is exactly at the center, means the radius of the cylinder is r. There is equal distance on all sides. So it is symmetrically distributed on all sides. Then let L is the length of the cylinder, R is the radius. So the length of the cylindrical Gaussian surface and R is the radius of it. And line charge is present exactly at the center of it. Now, whenever there is a line charge, definitely there will be electric field intensity. With point charge, there is electric field intensity. Even with line charge also, there will be electric field intensity. Suppose if you keep a charge here, it experiences electric field intensity. Either it is attracted or it is repelled. So that's what is electric field intensity. How much of electric field due to this line charge we want to find out. So that's the motive. Now, there is no way that you can calculate this with the help of Coulomb's law. The only way out is you have to approach the Gauss law of electrostatics. Now, if you see in Gauss law, the important thing is considering the ideal Gaussian surface, which is ideal Gaussian surface in case of line charge, it is the cylinder. Now, what is the mathematical treatment? We always start with the Gauss law. That is integral EDS is equal to Q by epsilon naught. Now, there the charge was Q. There means in case of point charge, the charge was Q. But here it is line charge. Therefore, we have to convert Q in terms of rho L, which is line charge. So we can't directly write Q because it's not the isolated point charge, but it is a line charge, one-dimensional charge. So the logic is same. Uh, Density is mass by volume. Charge density means charge by volume. Line charge means charge per unit length. Charge is Q by length is L. Suppose if you take elemental length, you will have elemental charge dq. So therefore, dq is equals to rho L dl. Means that is what is seeing here. Rho L is equals to dq is equals to rho L dl. Now that is what is dq. but we want q, means you integrate dq, integral of dq is q. Q is equal to integral of rho L dl. So what is this limit 0 to L? Because the length of the cylindrical Gaussian surface is 0 to L. So if one side of the cylinder is 0, the other side is L. Okay, so now we can't write Q, it is line charge, therefore Q must be modified as rho L dl. This is a slight change when you compare this with the point charge. In point charge, directly we have taken the Gauss law as integral EDS is equals to Q by epsilon naught, but in this case, we have to consider it as rho L dl. Now, what I am doing is, this is very, very important. Previously also I told you what is the direction of the electric field and what is the direction of the surface, normal drawn to the surface. This direction we have to see and check what is the angle between them, and that angle will decide which are the contributors that we have to consider and which are not, which we can ignore. Now there are three surfaces here. One is, you may say this is front, this is back, or you may say left side and right side. So these are the two surfaces. These two surfaces are identical, they are circular in nature, both are circle. And there is this cylinder, this round one. This one is called as a radial surface. There are three surfaces. Two are alike, the front and the back, or we say the left side and the right side. They are two circles, and these two circles are identical in nature. We have written mathematically as front and back here, and there is one radial surface. So what I am saying is this front and back contributions are zero, whereas this radial contribution is non-zero. Why is the question? One should know. I was just mentioning that which surfaces can be considered, which surfaces become zero, can be ignored. Now you all observe that what I have done is I have considered an elemental surface on the cylinder, that is the radial surface. Electric field due to this charge is in this direction, and normal drawn to this is also in the same direction. So when the two are parallel to each other, the angle between them is 0. Cos 0 becomes equals to 1. Therefore, this contribution exists. That's why the radial component is there. And what is not there is front and back. Now let us say due to line charge, this is the electric field, and on this front or back, whatever you call, or left and right, this is the elemental surface and the vector. So how both make 90 degrees. Cos 90 is equal to 0. Let's take the elemental surface on this. This is the electric field direction, and this is the normal to the elemental surface. They make 90 degrees. So both this is 0 and this also is 0. Only the radial component is remaining. Okay, so this is one important thing one should always take care, even solving complex problems, that which components exist, how to decide. You have to check what is electric field and what is the normal drawn to the elemental surface which you have considered. Now, as only one component is remaining, E ds cos theta, that cos theta is 1, and E comes outside. So what is remaining is integral ds. Which surface we are considering? Not the total surface area of the cylinder, only the radial surface that we are considering. So E is there, the radial surface is 2 pi r L. Why 2 pi r L? 2 pi r is the circle, means if you take the cylinder, how much circumference it has, and L is the length. So 2 pi r into, actually we write h is the height of the cylinder, we write 2 pi r h. So now what is remaining is E into 2 pi r L is equals to Q by epsilon naught. Actually, that q by epsilon naught we have changed as in integral form, but one way of writing is if you take it as q, then E is equals to q by 2 pi rl epsilon naught. So that's the formula for electric field intensity due to an infinite line charge. Now we want to write it in terms of rho L as mentioned, because even in problems, if it is line charge density, they'll give in terms of rho L. However, if you know rho L and L, we can calculate Q, or if you know Q and L, you can calculate rho L. All these are interconnected. So if you cross multiply epsilon, it becomes d is equals to 2 pi RL. Now, I mentioned in the beginning that infinite line charge, if you know rho L, that length doesn't matter. Now we all see that Q is equal to rho L into L, the same logic. Line charge density is equal to charge per unit length. So L comes to the denominator. So from that statement, you will write this. So wherever there is Q, you will write as rho L into L. So that L gets cancelled. What remains is E is equals to rho L. Rho L is the line charge density by 2 pi r epsilon naught. So what is 2 pi? You know, r is the radius of the cylinder, cylindrical Gaussian surface. Epsilon naught is the permittivity of the free space. If epsilon naught is multiplied, then what happens is you get the value of d rho L by 2 pi r. If you know the rho L, means essentially the length of the infinite line charge, we are not bothered. We are only bothered about how much charge is present per unit length. The same charge is replicated across infinitely. So therefore our major concern is how much charge per unit length. If you have more charge per unit length, you'll get more electric field. If you have less charge per unit length, less electric field. If you have no charge per unit length, no electric field intensity. So as simple as this. So if it is uh, line charge of L or line charge of infinite length, it doesn't matter. Essentially what matters is how much of charge is present per unit length. So compared to the point charge, what is the difference you observe? Point charge means you write as Q, but line charge means you will write as rho L. Therefore, Q we have converted in terms of rho L. That's the first change. And second is we have considered the Gaussian, cylindrical Gaussian surface, which is different from the spherical. So cylindrical because it's line charge density. And the third difference is we didn't take all the surfaces. We tried to see what is the angle between the electric field as well as the normal to the ds, and then decided which components remain and which components become zero. Now let's look at the surface charge, which is the third. You have a surface charge which is two-dimensional charge spread across two dimensions. In this case, it is spread across xy dimension, xy axis, xy plane, I can call it as, and z axis is perpendicular to it. So the surface area of that is A, and the charge density is rho s. If it is line charge, we have written as rho L. If it is surface charge, we write it as rho s. And then what type of Gaussian surface we need to consider? It is the rectangular Gaussian surface. It's just like a cube or cuboid with blue dots, which you can see across here. And what is that thing is two of its faces are parallel to the sheet. Means the top one and the bottom which you are seeing are parallel to the infinite sheet. So that's the description. It's again an infinite sheet of charge. You will also see whether it is finite or infinite, what matters. Now what we are trying to see is with this infinite sheet of charge, suppose let us say I have kept a unit positive charge here. definitely there will be electric field experienced by this positive charge. And once again, I say that this is infinite sheet of charge or infinite two-dimensional charge spread across two dimensions. Nowhere you can apply the Coulomb's law and find out the electric field intensity or the force between the two charges. We have to go for only the Gauss law of electrostatics. So one important thing you should remember is that the top and bottom surfaces of this Gaussian surface are parallel to the infinite sheet. So what is that we have to do? The three steps we follow again here. One we have already followed, the Gaussian surface that we consider is different from the first two. One is spherical for point charge, a cylindrical for line charge, and this one a cuboid type of surface, Gaussian surface. The second one is you can directly start the mathematical part, start with the Gauss law of electrostatics, but instead of Q, we have used rho L for line charge. Here we have to use rho S for surface charge. That's another modification. Now, for a spherical surface, first point charge, there was only one type of surface. Whereas in case of cylindrical, two circles at the end of the cylinder and one radial surface, front and back and the radial. The front and back were 0 and the radial was existing. Similar type of analysis we will do here. Now if you see, this is what the Gauss law of electrostatics, and we have written Q as rho s ds, rho s into A. The same logic here, surface charge density is equal to rho s is equal to uh, charge per unit surface area. Okay, so it's as simple as charge density is equals to charge by length. In the previous case here, charge by area. If you have volume charge, then charge by volume. So in this case, it's only area because it's two-dimensional. So that's how we have written Q is equals to rho s into A. So wherever this Q is there, we can write now rho s into A. Now, how many surfaces are there here? 6 surfaces. Even if you consider it as a cube or a cuboid, whatever it is, there are 6 surfaces, out of which we have understood that the top and bottom surfaces are parallel to the infinite sheet. Only the top and bottom. Now, what is the advantage? This is the direction of the electric field, and if you consider the elemental surface ds, both are parallel. Now, even for the bottom also, both are parallel. Electric field is in this direction. Um, both are parallel to each other. Therefore, the contributions due to top and bottom remain. What are the other things that are there? If you think this is front side, that will be back. If you think this is left side and this is right. Let's take one of them. So electric field is in this direction and this is, so the angle is 90 degrees. If you take this as a surface, ds is along this direction, electric field is along this direction, 90 degrees. Wherever you take this, for left side, right side, front and back, the angle made is 90 degrees. You know what happens if it is 90 degrees? If it is 90 degrees, cos 90 becomes equal to 0, whereas only for the top and bottom, both are parallel, becomes 0, cos 0 is 1. So what contributions remain is the top and bottom contributions remain. So that's why the other contributions, other 4 contributions, we made it as 0. Only the top and bottom contributions remain. So the 3 things we have done here also again. The first thing is identifying the right Gaussian surface. Second is, rather than writing Q in the Gauss law, we have written in terms of surface charge density, rho s. The third thing is, out of the 6 surfaces, how many are remaining? I mean, how many actually contribute, how many don't contribute? How do we know that? Based on the angle made between the electric field and the normal drawn to the elemental surface. considered across that surface. So eventually only two remain. Now the problem is simple. So cos 0 is 1, therefore EA for the top into A for the bottom, because integral ds is there. So integral ds is the top surface area A, bottom surface area is also same. What we get is twice of EA is Q by epsilon naught. So E is written as Q by 2A epsilon naught, means you are isolating E, 2A goes to the denominator. And if you take epsilon naught to the other side, it is what is your D. D is equal to Q by 2A. Now what we have to do is, as we have done in the previous case, instead of Q, we have to write in terms of rho S. So we know already Qs is equal to rho S into A. So what it becomes is, instead of Q, what we have written, rho S into A. So A and A gets cancelled, rho S by 2 epsilon naught remains, and epsilon naught goes to the other side. This is what is your D. So if you look at these two expressions, you will understand that the area doesn't matter how large the area is. Is it in infinite or finite? Doesn't matter. What matters is rho s. How much of charge is present in a given unit area? That's what is matter. If you know rho s, then everything else, even if it is infinite, it is the same. Finite or infinite doesn't matter. So essentially it is the how much charge is there spread across in a given unit area that matters the most. So these are the key steps that one needs to follow. First is identify the proper Gaussian surface. Second is that which are the contributing surfaces, which don't contribute. That is decided by the angle between the electric field and the normal drawn to the ds. That's the second one. The third one is, if it is line charge, if it is surface, if it is volume charge, you can't present in terms of Q, but rather rho L, rho S, rho V. So that conversion needs to be made. So this is what lecture summary. Through this video, you have understood the construction of Gaussian surfaces for simpler problems like point line surface charge distributions. And with this idea, with these three steps which I was emphasizing, you will be able to apply Gauss law to any other different types of charge distributions. The importance of these three steps one understands when they start solving problems using Gauss law of electrostatics. Thank you.